Facial animation plays the most substantial role in depicting expressive human characters in a virtual world. The face has many muscles, which move and express the person's emotion in various ways. Realistic and expressive 3D face animation is challenging but essential for a virtual character in computer animation, films, computer games, and virtual reality VR. Therefore, researchers have studied facial animation methods intensively for the last several decades. In the 90s and noughties, researchers successfully rendered realistic facial animation through advanced performance capture animation and rendering techniques. Realistic facial animation was good for films, computer animation, and games. However, despite this progress, the existing computer-synthesized human facial animation still requires costly resources and sometimes involves considerable manual labor. Post-processing was a must for realistic facial animation. Nowadays, online facial animation without post-processing becomes more demanding due to intelligent characters in VR and metaverse. Hence, one of the interests in modern research is generating facial animation with minimal human labor or fully autonomous real-time generation facial animation. This survey aims at providing a survey for the modern audio-driven lip-sync 3D animation methods. The survey is carried out in two most notable areas: linguistic-based animation and deep learning-based animation. In addition, the survey also provides a historical view of the evolution of these techniques. Section 2 covers the history of facial animation research, Section 3 presents the linguistic-based facial animation, Section 4 describes the learning-based facial animation, and Section 5 concludes. 2. Brief history of facial animation. Research on realistic computer-generated human face animations has received interest in the last few decades. One of the pioneering works in the field by Parzok in 1972 used two PDP-10 computers, which have 1 flops of computing power. Despite the limitation of low-power computing of the era, the method successfully interpolated between facial expression mesh, rendering 20 animation frames per hour. On the other hand, Frederick I. Park created the first 3D parametric model of a human face in 1974. Later in 1980, face deformation research was addressed. Platt and Badler described the muscle-based method that constructs expressions using a muscle-based facial model, using the facial action coding system FACS, a facial action coding model from psychology. Walter Kay introduced a deformable model that deforms mesh based on a deformation function based on muscle autonomy. Tertsopoulos et al. Applied the physics-based method to the face model, which implements physically based muscle and other layers to simulate facial autonomy further. To animate a face realistically, especially a human talk, synchronizing animation and speech audio is a significantly important task. Lewis and Park's lip-sync system automatically breaks recorded speech into phonemes and then animates the mouth shape of a parametric model. Consequently, Cohen and Massaro produced a lip-sync system using a parametric model in 1990, based on the context of speech perception. They later extended the model to include a tongue and to model co-articulation effects. Co-articulation is a complex behavior of articulation of multiple voiceme overlapping and affecting each other. Simultaneously, performance-driven animation gained considerable attention. In 1990, performance-driven animation was first introduced by Lance Williams, which used a single video camera to capture markers on the face. Capturing an actor's face digitally and animating based on the actor's performance resulted in a photorealistic 3D animation. Gunter et al. Used video streams from 6 high-resolution cameras to capture facial motion in 3D in 1998. A more delicate algorithm also involves using an expression ratio image ERI to create fine details such as face wrinkles. Then in 2003, vision-based research captured facial movements from a single video like research by Chai et al. 3. Vision-based face, JALI. JALI is a state-of-the-art ViSeam model that generates lip-sync animation from audio signal and transcript. Unlike other methods, artists can quickly edit and refine sparsely keyframed JALI animation. JALI model is based on the observation that one can aggregate its attendant facial motions into two independent categories, functions related to jaw motion and lip motion. Altogether, JALI's goal is given an input audio soundtrack and speech transcript, generate a realistic, expressive animation of a face with lip, tongue, and jaw movements that synchronize with the audio soundtrack, where animators can easily edit the animation. JALI ViSeam model is motivated by the directly observable bioacoustics of sound production using a mixture of diaphragm, jaw, and lip. The traditional approach to lip-sync animation overlooks that phonemes in speech change based on phonetic context and speech styles. When we hyperarticulate, i.e., over-enunciate, we form ViSeams primarily with lip motion using facial muscles, with little or no jaw movement. Conversely, when we hypoarticulate, i.e., speak in a drone, we primarily use jaw/tongue motion with little or no lip action. Thus, JALI maps each phoneme to a 2D ViSeam field along nearly independent jaw and lip axes that capture a wide range of expressive speech. The ViSeam to be keyframed is determined by a co-articulation model, which contains constraints of articulation, speech convention, and co-articulation habits. Next, in the force alignment phase, ViSeam's timing is determined. Moreover, the jaw/lip multiplier is determined by lexical and word stresses returned by the phonemic parser. Then ViSeam animation is multiplied by the animated jaw/lip multiplier. Compared to commercial performance capture animation, the result shows that JALI animation has 32 times fewer points. Additionally, a short, informal study was performed. For animators completed tasks to refine and edit hand-generated animation, JALI animation, and motion capture data. All animator participants rated motion capture data lowest for ease of use while preferring JALI, and hand-generated animation similarly. In summary, JALI presented a novel animator-centric workflow for automatically creating lip-synchronized animation. JALI became commercially successful, notably used in the game Cyberpunk 2077. Additionally, ViSeminit utilized a jaw/lip multiplier to learn the ViSeam model with only auditory data. 4. Deep learning methods. Improvements in performance capture methods allowed researchers to collect a sufficient amount of quality datasets, allowing exploration of deep learning methods. Modern convolutional neural networks have proven highly effective in various inference and classification tasks, and they tend to regress toward the mean if there are ambiguities in the training data. Moreover, the hidden Markov model or recurrent networks shows strength in processing sequential auditory data. Karras et al. Introduced a machine learning technique to drive audio-driven 3D facial animation in real time. The presented network takes a neutral mesh and learns to animate a facial mesh with an audio signal, and an encoded emotional state. Produces expressive 3D facial motion from audio in real time with low latency. A mesh talk. Psychological literature has observed a dependency between speech and facial gestures. However, audio does not encode all aspects of facial expressions. Thus, the audio-driven facial animation problems try to learn a one-to-many mapping, i.e., multiple plausible outputs exist for every input. This one-to-many mapping often leads to over-smoothed results of the deep learning lip-sync model, especially in the regions of the face that are only weakly or even uncorrelated to the audio signal, as seen in the VOCA model. Meshtalk tried to overcome the over-smoothed results and proposed a novel audio-driven facial mesh animation approach that enables highly realistic motion synthesis for the entire face and generalizes to unseen identities. The goal of the Meshtalk is to animate an arbitrary neutral face mesh. Since speech does not encode all aspects of facial expressions, Meshtalk Richard et al. Suggests a method to learn a categorical latent space for facial expressions. A sequence of animated face meshes, the expression signal, and a speech signal are mapped to a categorical latent expression space. Then a UNIT-style decoder is then used to animate a given neutral face template mesh according to the encoded expressions. Disentanglement of speech-correlated and speech-uncorrelated information is crucial. For example, eye closure should not be bound to a specific lip shape. So, Meshtalk Richard et al. Propose a cross-modality loss that ensures latent space utilizes information from both input modalities. Reconstruction of audio and expression signal is done separately. The cross-modality loss is defined as a sum of separate L2 loss for each signal, each vertex multiplied with weighted masks. For audio, the weighted mask assigns high weight to vertices around the mouth and low weight to other vertices, and vice versa for expression. Since eye blinks are quick and space events, adding additional eyelid-specific loss was crucial. Cross-modality loss is the sum of audio, expression, eyelid-specific losses. Meshtalk Richard et al. Conduct multiple tests to validate methods to disentangle auditory and expression signals, the most apparent test being the visualization of latent space 3. Furthermore, the test result is compared to VOCA numerically and perceptually to evaluate the network. Numerical analysis showed a more accurate lip reconstruction and significantly better favorability over VOCA. Discussion. In this paper, we described the techniques used in lip-sync facial animation. First, we introduced the history of facial animation, then, JALI, the modern high-end linguistic model which generates animator-centric keyframed animation, and the deep learning method Meshtalk, which generates a full facial mesh. JALI automatically generates expressive lip-synchronized facial animation with an input audio soundtrack and speech transcript. The low dimensionality of the resulting animation enabled artists to edit and refine animation quickly. However, the model lacks some co-articulation behaviors from observations such as fast versus slow speech and lacks emotional speech styles. These features can be added to co-articulation rules to improve the model further. Meshtalk Richard et al. Is a generic audio-driven facial animation approach that achieves highly realistic motion synthesis results for the entire face. Meshtalk Richard et al. Use categorical latent space and novel cross-modality loss to disentangle audio-correlated and audio-uncorrelated information to ensure high-accuracy lip motion while generating plausible animation for parts of the face unrelated to the audio signal. However, if the facial tracker fails to track specific parts of the face, like hair overlapping eyebrows, the model cannot learn the correlation of the facial mesh. Audio-based methods required additional emotional mesh to articulate other than lip-syncing animation. Meshtalk Richard et al. Needed additional expression mesh and Karras et al. Required an emotional vector to generate facial animation, while JALI only animated facial parts around the mouth. Due to the current limitation of the audio-based approach, it is inevitable to require additional expression data other than audio. The task of extrapolating expression data from human speech is challenging and will need further investigation.